Good day to everyone. So in the last unit, we have discussed about the one of the property of the fluid, which is called the viscosity. So we have studied about the viscosity of the fluids and how to determine the coefficient of viscosity with the different methods we have seen in the last unit. So in this video, we are going to begin the to study about the unit 5, that is the fluid dynamics. So in this fluid dynamics topic, we are going to study about the pressure of the fluid. That means, suppose if you take a fluid in a container and how this pressure of this fluid, which is affecting the submerged objects into this fluid, and we are going to derive the equation for the thrust and the center of pressure of this fluid. And suppose the object submerged into the fluid is actually maybe a rectangular shape or a triangular shape, we are going to derive the center of pressure of the corresponding shape of the body. Similarly, how this the atmospheric pressure is varying with respect to the altitude, the equation of continuity, and the Euler's equation for the unidirectional flow of the any liquid. And based on this, you have to derive a theorem which is called the Torsles theorem, and we are going to study about another theorem which is called the Bernoulli's theorem, and we are going to apply this Bernoulli's theorem and discuss about some of these applications. First, we begin with the pressure. So in the starting of this unit 3, we have discussed about the pressure of this fluid and derived the derivation for the pressure of this fluid. Now what we are going to do is we are going to take a fluid in a container, so that the container is filled with any water or any fluid, and the fluid which you have taken is actually in contact with the atmosphere. So how this the pressure is actually varying once we are going into the liquid, and how the depth is actually affecting the pressure of the liquid. Everything we are going to see. Okay. So first we are going to study the pressure of the fluid which is at the rest position. So fluids at rest. So we are going to take a container. So we are taking the container, and this container is actually filled with the water, and this water is actually filled with some height h. So as we know that suppose if you are suppose this is taken as a reference point, that is the point which the water and air is actually meeting. So this is the surface which I can take in this y equal to 0. That means the y axis is taken as 0. There is a reference point I can taken. So once if you are moving above this point, then the positive signed values which is increasing, and if you are moving inside this water, then the value of y is actually decreasing in the negative direction. It is considered this is the case. So as we know that once if you are moving inside this water, then the pressure is actually increasing. Once if you are moving into the depth is increasing. Similarly, suppose if you are moving in opposite direction, that means in the air. Suppose if you are moving in upward direction, then the pressure is actually decreasing. So this can be explained. This can be imagined that suppose if you are some person is actually diving into this pool, water tank, water pool, or a swimming pool, then suppose if you are going inside the water tank, then the pressure is actually increasing. Similarly, suppose if a mountaineer is actually climbing a mountain, then the pressure is actually decreasing once the altitude is actually increasing. So the pressure which we are actually talking here is actually called a hydrostatic pressure. So hydrostatic pressure, that means the fluids are at rest. That means when you are studying the pressure, the fluids which we are considering is at rest position. So in this case, we are actually find out the expression for this hydrostatic pressure as a function of the altitude or depth. So I'll start with, let us first looking into the increase in pressure with the depth as below the water surface. So in the y-axis, this point, so the y equal to 0 is actually representing the contact of the air and water, which is interface with the air-water interface. and if you're moving above this axis, above this reference point, then as I again told you, that is a positive valued increase, and if you're moving downwards, then it's a negative y direction. So next, what I'm going to consider is I'm going to take a small area of this water, an imaginary layer of water which is having the horizontal base, which is having the area of A. So the y1 and y2 actually representing the depth below the surface of the water. Both y1 and y2 having the negative values because it is actually having the negative y direction. So the y1, y2 having the negative values. So the y1 represents the upper face of the cylinder, the upper face of the layer, and the y2 represents the lower face of the layer, the lower face of the water layer which we are considering. And P1, P2 are the pressure at the layers y1 as well as y2. So we consider that this water is actually in the static equilibrium, then that is the liquid actually is in a stationary position, so that the forces acting on the liquid is actually balanced by the different forces. Suppose if you consider this small imaginary water layer, then there are three different forces are acting on this water layer. One is the first is the force acting on this top layer due to this water above the layer, so that this water above the layer is actually producing the force which is actually downward, acting downwards, which is taken as a F1. So the second force acting on this bottom layer. So due to this water just below the cylinder below this water layer, so that there is a force acting upward, it's an upward force acting on this second layer, that means the bottom layer, due to the water available in this tank, suppose which is taken as a F2. So both F1 and F2 are actually vectors. So apart from this, there is another force. There is a gravitational force which is acting acting downwards, G, which is equal to the gravitational force which I taken as a m times of G. So the m is the mass of this the small sample which we have considered. So since this fluid is at the static equilibrium, all these three forces are in the imbalance, so that I can just schematically write this forces as suppose if I consider this is a sample, then the first force acting upwards, that is a F1, and another force which is actually the first force acting actually in downwards, that is the F1, and there is another force acting in the opposite direction, F2. Similarly, the third force is acting again on the downwards, which is a gravitational force. So at this equilibrium point, all these forces must be equal each other. So the balance of these three forces can be written as F2, which is equal to F1 plus m into G. It means the force F1 and mg is actually acting downwards, so that which will be equated by the force F2, so that F2 which is equal to F1 plus mg. Okay. So as we already know that the force can be written in terms of force is nothing but the pressure into area. That means the pressure can be written as force per unit area, so that I can write F is equal to pressure into the area. So suppose if you consider just writing the force in terms of pressure, then I can substitute the values of F is equal to P into A in both in this equation 1. So I can write the force 1, F1 can be written as P1 into A. Similarly, the F2 which is equal to P2 into A. So this P1 and P2 are the pressure difference, the pressure at this top layer and the bottom layer of the sample which we have sample of the water which we have considered. And once if you're looking into this force, the gravitational force m into G, so the m is the mass of the water layer which we have considered, so that I can write this mass is equal to density into volume, where the layer water layer. So here this volume is the product of the faces of the area multiplied by the height. Therefore, I can write the V is equal to area times the height can be written as y1 minus y2, because the y1 is the the top layer and the y2 is the y2 bottom layer, so that I can write this as a y1 minus y2, so that this m is equal to rho v can be written as rho into a times of y1 minus y2, so that I can substitute all this f1, f2 and this mg values, that is m is equal to, so the value of m is equal to given, like suppose I conference by mg, I can write this as a rho into a into y1 minus y2 in times of g, so that I can substitute this by f1, f2 and mg values in this equation. So I can write it as, so p2a which is equal to p1 times of a plus rho into a g times of y1 minus y2. So if you take a as the common and common at both sides, so I can take the cancel out all the areas here, so that I can write p2 which is equal to p1 plus rho times of ag y1 minus y2. So this is the equation number 2. So which is the pressure of this. So this equation used to find out the pressure. So this equation can also used to find the pressure in both liquid as well as the atmosphere. Suppose if you consider the liquid, then as a function of the depth, or if you consider the pressure of the atmospheric pressure, then you can as a function of the altitude. That means the difference in the height. So in the case of liquid, suppose we seek a pressure, the pressure as taken as a P at a depth of some height h, some depth height below the liquid surface, then we can choose the level. Then we can consider this is the y1 is taken as the surface, and similarly this point, this is the y2 is actually taken as the y2 is actually situated at the distance from a function of with the height of h. And if we consider the P0 is the atmospheric pressure of the surface, then we can substitute y1 equal to 0. That means this is the reference point. The y1 is the reference point, and similarly the P1 is the atmospheric pressure. That means at this point we can take it as the atmospheric pressure. So P1 is equal to P0, and y2 which is y2 which can be written as minus h because of this the negative variation, and similarly the P2 can be written as P. Suppose if you substitute all these values in this equation, then I can get P equal to P0 plus rho times of G into H. Sorry, here the A will not come because A is cancelled out in both the direction, both the sides. So the rho times of G. So rho G into this the difference with the taken as the height. So this will be the equation of to find out the pressure at a given depth of the depth at H of the liquid depends upon the height of the sample which we are actually considered. Okay. Therefore, from this equation we can identify that the pressure at any point of the fluid in a static equilibrium, this depends only on the depth of the point which is actually situated in the liquid, but not any horizontal dimensions of the fluid or its container, which is the container which is actually situated, the fluid is actually situated. Okay. So the pressure is actually only depending upon the depth of this the vertical depth of the point. So therefore the pressure of the container is not depending upon the pressure of the liquid is not depending upon the container it is actually holding, but it is only depending upon the height of the corresponding point at which the object is situated. So here this P is actually known as the total pressure or a absolute pressure. At the bottom of this surface, if you take this at this point, this pressure is actually known as absolute pressure, because at the bottom of this the layer, the pressure is actually consists of two contributions giving the two different contributions. One is the atmospheric pressure, which is taken as P0, and the pressure due to the atmosphere, and with the rho times of G into H, which is the pressure due to the liquid above the bottom layer. So in general, the difference between this absolute pressure and the atmospheric pressure is called the gauge pressure, which is also known as the gauge pressure, which is nothing but the difference between the absolute pressure and the atmospheric pressure. Suppose if you want to find out the atmospheric pressure at the given distance above this the upper layer. For example, this if they consider this layer, and the P1 can be written as P1 is assumed as the atmospheric pressure, which is equal to P0. Then I can write this equation, the equation which we have found, this equation 2 as, suppose if I consider so the y1 is the reference point, so that I can take y1 is equal to 0. Similarly, the P1 equal to P0 and y2 is equal to having some depth of d, and P2 which is equal to P. Then I can write this equation as P equal to P0 minus times of rho into G into D, where this rho is the density of the air, so that I can write this as rho into air. So I can write this up to rho subscript air into G times of the distance, the depth, with the distance d above this, above the first layer one which you have considered. So this equation can be used to find out the atmospheric pressure at a distance of the distance d above the level, above the top layer. So using both these equations, I can find out the pressure inside the liquid and also the atmospheric pressure using these two formulas. Okay, so as I already mentioned that the pressure of this fluid depends only on the depth from the surface, and not depending upon the shape of the container it is having. So therefore, if you take any container and if you pour the fluid into this container, then the fluid can freely move into the various parts. Therefore, if you consider the container like this, and if you pour the water liquid into this container which is having the different shapes, then the fluid will freely move in the various parts of this container, and it stays with the same level of height in every part of this container, regardless of the shape of the container. And even though if you consider the pressure force, which is actually having a vector quantity. Suppose if you consider the pressure doesn't have any direction, so it is actually a pure scalar quantity. However, this forces due to this pressure is actually having the well-defined direction. They are always exerted perpendicular to any surface. So the reason for this is that the fluid cannot withstand or exert any shearing forces. Therefore, the static fluid enclosed in this tank. Therefore, in a static fluid enclosed in a tank, the force exerted on the walls on the tank is extended perpendicularly to the inside surface of the inside surface of the container. Similarly, the pressure exerted perpendicular to the surface of any object within the fluid. For example, if you consider a tube which is actually filled with an air, then the force is actually trying to push the force due to the pressure is actually exerted perpendicular to the surface of any object. Therefore, suppose if you are trying to send the air into the tire through this valve, then there is a small the opening here which is actually allowing the air to go inside. And suppose if you remove this pressure, then due to the pressure difference, the inside pressure is actually higher than this outside pressure, so that the inside pressure is actually trying to acting on the perpendicular to this direction, so that the air cannot come outside, even if the outside of the valve is still open. And similarly, the forces due to the pressure inside the tire is actually acting on the walls of the tube. So coming back into this picture, which is the property which is showing in this picture, that the vertical height of this column of the liquid, any liquid which is remains same, the pressure exerted is actually remaining same irrespective of the actual mass, weight, or the shape of the container. So based on this property, Pascal discussed his results. So that is called, he actually defines a certain results using his laws, which is called the Pascal law or Pascal principle. So he considered the different vessels with the different shapes, but having the equal bases which is actually kind of taken, and if you fill with the liquid up to some vertical height h, so that the pressure of this base of each vessel was equal, and based on this he actually given the Pascal principle, and this principle says that a change in the pressure applied to an enclosed incompressible fluid is transmitted undiminished to every portion of the fluid and to the walls of its container. So that is what the Pascal's principle says. So knowingly or unknowingly, we are actually using this Pascal principle, and at every day of morning, suppose when you are squeezing the tube of the toothpaste on one end, then you can get the paste on the other side, which is actually working as a paste on the principle of this Pascal's principle. And suppose if you want to demonstrate this Pascal's principle, we are going to consider the case in which we are going to consider the incompressible fluid. That means, suppose if you apply any pressure on this liquid, the liquid will not compress. That is called the incompressible fluid. So we have taken the incompressible liquid in the tall container. So the cylinder is actually fitted with the piston, on which the container on which we have a load. That means the weight is actually kept on the piston. So when you put the weight on this piston, then the pressure is actually exerted on this liquid. Since the liquid is actually incompressible, there is a force acting. There is a pressure is actually acting on this liquid. Suppose this pressure exerted at this point is taken as a PEX, and you are taking any point in this liquid. Let us say I taken the point P, which is actually situated at some height of h. Then I can write the pressure P is equal to the pressure exerted by this weight PEXER plus the pressure due to this liquid, which I can write as density into G times of h. So this will give you the pressure at the point at any point P in this liquid. Suppose if I add more weight onto this container, then the the external pressure is actually changed to some other amount. Let us take this external pressure, the change in external pressure taken as the change in external pressure. Let us take this change in external pressure as taken as delta PEX ER, the external pressure. So even though I am adding a weight on this piston, the density and the height will not change, so that this remains constant. Therefore, I can write the change in pressure as delta P, which is equal to delta P times of EXER. So this pressure change in pressure is actually independent of the height, so it must hold for all the points within the liquid as per the Pascal's principle. So that if you are taking a point here or wherever, that is actually depending upon this height. Sorry, independent of height, the pressure due to this weight is on this liquid is actually equal on the all part of this liquid. So this principle is actually having the interesting consequences. And one important application of this, the Pascal principle, is the hydraulic lever. So in order to show how this the Pascal's principle is actually used in the hydraulic lever, so for the operation, let us consider the hydraulic container which is having this shape, where the input side we have the area is actually given as AI, and the output area, that means this container is actually filled with oil, and this is one piston, the first piston which is giving the input piston, and this is another piston which is actually the output piston, which is the input side which is having the area of AI, and the output side is having the area of A0. Usually the A0 is much larger than the AI. Suppose if the external force of magnitude Fi is actually directed downwards in the left hand side of this piston, so if you apply a force of input force of this point, and the surface area is actually given as AI, since it is actually contain the incompressible fluid, so which is actually producing the upward force of magnitude FO on the right hand side of this apparatus, which is having the area of A0. So to keep the system in equilibrium, there must be a downward force of magnitude FO on the output piston from an external load acting on the hydraulic lever, so that this force Fi is applied on the left hand side of this apparatus. Therefore, on the downward force of F0 from the load on the right side of this apparatus, which is actually making the pressure difference, which is taken as a delta P in the liquid. So that I can write this pressure difference for this container, I can write the P delta P. This is equal to the Fi divided by AI, which is equal to F4 divided by AO. So that is the pressure difference. So from this equation, I can derive the output pressure, output force F4, which is equal to F5 times of AO divided by AI. So this equation shows that the output force F0 is actually F0 on the load must be greater than the input force if the A0 is greater than AI in this case. Suppose if I consider this the input piston, the input force is actually moving the piston with some distance d I, then the output piston on the other direction is actually moving upward with some distance do, so that the same volume of incompressible liquid is actually displaced from the both sides, so that I can write this volume, which is equal to the area into the total area into the distance which is the liquid is moved. You can write as AI di, which is equal to AO into DO. That means which is equal. That means the volume which is displaced from this point is actually same as the volume displaced in the other direction, so that I can equate the volume of these two sides as like AI into DI. This is equal to AO into DO. So from this equation, I can write this expression in terms of DO. So DO, which is equal to DI into AI divided by AO, which shows that if the A0 is greater than AI, as shown in this figure, then the output piston moves in a smaller distance than the input piston moves. Okay, so the input piston actually moving in the large distance. However, due to equate this volume, only a small portion of this piston is actually only the piston is actually moving with a small distance of d0 to equate this to maintain the equivalence. Therefore, I can write the work done to move the piston on the right hand side to d0. So the work done W, which can be written as the force into the distance moved. The force is actually F0 and the distance moved is the d0. So that I can just substituting this F0 and d0 into this equation. F0 is nothing but the F5 times of A0 divided by AI multiplied by the di times of AI divided by A0, so that this A0 AI will get cancelled, so that W, which is equal to F0 D0, which is equal to F5 into di, which shows that the work done on the input piston by the applied force is equal to the work done by the output piston, which is actually lifting the load on the load placed on it. Therefore, the advantage of the hydraulic lever is, with this hydraulic lever, a given force applied over a given distance can be transformed to a greater force applied over the smaller distance. Therefore, if you apply a force this left hand side, and if you move the piston for some distance, that will be actually exerted the force which will be exerted on the oil, which is actually causes a very huge force applied on the which is actually on the the right hand side. Therefore, the product of the force and distance is unchanged in both the left hand side as well as right hand side. So there is often a tremendous advantage of being able to exert this larger force. So suppose if this force is actually used in the hydraulic levers or in a hydraulic jack to lift the any automobile like car or any massive vehicles. So based on this, the Pascal's principle, this hydraulic levers and hydraulic brakes are working. Now let us discuss some of the problems based on this Pascal's principle. The first problem is, so in a hydraulic system, a piston with a cross-sectional area of 21 square centimeter pushes on an incompressible liquid with a force of 38 Newton. So the other end of the hydraulic pipe, which is connecting the second piston with a cross-sectional area of 100 square centimeter. So we have to find out what is the force on the second piston. So we already know that according to the Pascal's principle, the force, the input side for F1, which is divided by F2, sorry, F1 divided by A1, which is equal to F2 divided by A2, where this F1 and A1 is the force and the cross-sectional area of the input piston, the input piston of the input side, and F2 and A2 are the piston, the second piston force as well as the area. So the values of F1, A1, A2 are given. So the value of F1, which is equal to 38 newtons, A1, which is equal to 21 square centimeter. Similarly, the A2 is given as 100 square centimeter. So we have to find out what is the F2 here. So that is what you have to find out. So you can just directly substitute all these values in this equation. I can find out this F2. So I can rearrange this equation in terms of F2. So F2, which is equal to F1 times of A2 divided by A1. So I know all these values in this direction, this side, which is 38 Newton. F1, A2 is given as 100 square meter, sorry, 100 square centimeter divided by 21 square centimeter. So this centimeter will get cancelled. So if I multiply those values, then the F2 will be equal to 180 newtons. Therefore, if we apply a 38 Newton of force, which is having the cross-sectional area of 21, and the output side, if you have the cross-sectional area of 100 square centimeters, then the force exerted is actually 180 newtons. It is around nearly 5 times larger than the input force applied on the first piston. So similarly, I can solve the second problem. The second problem is, so consider a hydraulic system with two pistons. The piston 1 is actually applies a force of F1 over the area of A1, and piston 2 applies the force of F2 over the area of A2. Suppose if you double the factor, the force applied by the piston 1 and reduce the area of the piston 2 by the factor of 3, so what is the new force exerted on the other side? So this is the question. So suppose if you consider the F1, A1 is the input with the old pressure, old force and the cross-sectional area, and the F2 and the A2 is the force and area of the pistons on the right hand side. And suppose if you change the F1 as doubled and reduce the area by 3, then I can write the values as F1 prime, that is a new force on the piston 1 is given as 2 times of F1 doubled F1, and you are actually reducing the area of A2 as by 3. So A2 prime, which is equal to A2 divided by 3, and the area of the input side is same, so that I can write A1, which is equal to A1 prime, which is equal to A1. Therefore, I can write the new equation as F1 prime divided by A1 prime, which is equal to F2 prime divided by A2 prime. And if I substitute the new values in this equation, I can write 2 times of F1 divided by A1 prime, which is equal to F2 prime divided by A2 prime is A2 divided by 3, or I can write this as 2F1 divided by, since A1 prime is equal to A1, so I can write this A1, this is equal to 3 times of F2 prime, so F2 prime divided by A2. So since F1 divided by A1 is equal to F2 A2, so I can just replace this as 2 times of F2 divided by A2, so that this A2 will get cancelled. So I get 2F2, which is equal to 3 times of F2 prime, or I can write the F2 prime as 2 by 3 times of F1. So which is the new force of which is a new force exerted on the other side of the system. Okay. So the third problem is, so a hydraulic system is used to lift a 2000 kilograms of vehicle in an auto garage. If a vehicle sits on a piston which is having the area of 0.5 square meter and a force is applied to the piston of the area of 0.03 square meter, so what is the minimum force required to apply? That means what's the minimum force that must be applied to lift the vehicle? So here the force, the input force and the input area is given, as well as the output area is given. So you have to find out what is the minimum force required to lift this 2000 kilograms of vehicle, so that according to the Pascal's principle, F1 divided by A1, which is equal to F2 divided by A2. So I can write in terms of F1. So F1, which is equal to A1 divided by A2 times of F2. So the F2 is not directly given, but we have given the mass with the weight of this vehicle, so that I can easily find out this F2 value with the value of F2. And if the values of A1 and A2 is known, the A1 is given as 0.03 square meter divided by A2 is given as 0.5 square meter multiplied by the mass into gravity, so that 2000 kilograms into 9.8 meter per second squared. Okay, so now I can easily calculate this will be equal to 0.06 multiplied by 19,600, so that I can get the value of 1176 Newton is the force. There is a minimum force required to lift this 2000 kilogram of vehicle. Okay, so I hope you understand this the Pascal's principle and the pressure acting on this hydrostatic pressure acting on this the liquid. So I stop here. Then if you have any doubts, then we can discuss in the online class. Okay, thank you.